Good. So, the punchline for all this is that for all the convex shapes which we saw, there are these two ways in which we can look at these things. Okay, and so this equivalence is kind of nice. The proofs are not really important for us, but it is good to see at least one proof. Okay, so what we'll definitely remember is that these spaces have multiple ways to understand. Right? We can think of them as convex or conic combinations, or we can think of them as in terms of inequalities. Now, we have this about the feasible set. Another thing we want to worry about is our optimization function, right? And our optimization function is also special. It's a linear function. In other words, it's a convex function as well as concave function. So let me define what a convex function is. Okay. Given 2 points x, y in the domain of f, a function is convex if okay. In some sense, so it's always good to view them in one dimension, and if you want to view it, what it says is that if you look at 2 points and draw the line between these 2 points, it is above the curve. Okay. This is the intuitive definition of function being convex. And then okay, and what are the functions which are both convex as well as concave? Linear functions. Yeah. Good that you know the geometry of it, but now we call them linear functions, right? And that means we can use this because our optimization function linear program is a linear function. That means we can use both, that our function is convex as well as concave. But why? Why is convex function nice? Or why is optimizing convex function nice? Just before that, why is it called convex function? Exactly. So if you look at the shape of this is called the epigraph, right? This is the set of all y such that all greater than or equal to fx, right? And for a convex function, its epigraph is convex. Okay? Great. Now we know what convex functions are, and the main reason why convex functions are nice is because global minimality is same as local minimality. Okay? What does it mean is that in general, let's say I have this function, right? This function is a local minima. What does it mean, local minima? If I move in any direction, my function value increases. So this is a local minima, but this is not a global minima. This is global as well as local. A global minima has to be a local minima. This is only a local minima. right? And why is it bad for optimization? Exactly. While we are optimizing, while we are changing directions, going towards the right, the best possible solution, we might get stuck in local minima. In other words, if we are optimizing or if we are minimizing a convex function from any non-optimal point, there exists a direction of improvement. Right? So wherever we are, if we are optimizing a convex function, we are minimizing a convex function, we don't have to worry. There is a direction where we can move and move towards the right solution. This is why this is so important. The convex function is so important.
It's not strictly true that you can have a function same local minima sort of function.
Oh, you are saying you are confusing between greater than equal to and strict inequality, and so even the same direction you can move, right? Without like you won't, okay, your function value direction where direction of not bad performance, is that what you want me to write? So he is worried about the case, simply put, if this is your function, then everything is a minima, right? And he's saying, oh, where do I move from here?
But he said it is non-optimal, right?
Sorry?
You have mentioned non-optimal.
So I think when we do this simplex method, we would want to go down to vertices. That's why, I don't know why, but yeah, this is not a problematic technicality. Okay. Good. So this is the important theorem for us, and let's try to see a proof of it. Okay. So I will show a proof for one dimension, and a similar proof can be extended for multiple dimensions. I want to keep my life easy and just give you an idea of how this thing works, right? So the first claim I want to make is that for a convex function, I can have another definition. This is the derivative at the x point x. Okay, and if it is multiple dimension, then this will be a vector, this will be a vector of derivatives, and then you take the dot product. But does this seem believable? Sorry? So for us, we will assume that they are defined by these nice inequalities and equalities, the space is nice. The function is, for us, the function is linear, so it has good derivative, but in general you can assume that your function has nice derivative. Okay. Again, this is not like 100% solid proof, it's one dimension, it's assuming things, it's just to give you an idea of why such a thing is true for a convex function. Okay, so I'm not saying that takes care of all the cases and everything. It is just giving you an idea of why this is working. Okay, why local minimality without global minimality can't exist for a convex function. Okay, so assuming the derivative exists, does this sound believable? Right? Other way to see it. Right? This is saying that the line y to x is above the tangent, right? So this you can. So now, let's say x star is your local optima, and for the sake of contradiction, or let's say y is another point. Right? What do I know from x star? If I move in any direction, my value increases. And now I want to show that fy is more than fx star. Right? Okay. So yeah, so this is where I always have less confidence, because this is something I did 20 years back. Right? Is that okay? Sorry?
So like we've expanded f prime x into this. So
Yes.
the denominator it should be
I, okay. So the main idea geometrically is, let's say x star is a local minima. If I want to look at the point, which is, so this is x star, this is y, what do? I move in this direction, right? And I know that the value is increasing, right? And if at y it comes down, the function doesn't remain convex. Right? Just this picture thing I have written like this.
how did we get the last conclusion?
From here to here, since this is a local minima, this quantity is positive. Right? So again, you look at x star is a local minima. Sorry? Oh, this is what you're saying? Yes, my handwriting, yes. Okay, so you start from x star, you move in the direction of y, even in the case of multiple dimensions, and you know that the value should increase. So if you just concentrate on that plane, if the value goes down, then your function is not convex. That's a problem. Okay? And any proof of this will formalize this argument. Okay? If you assume derivative is nice and everything, then this proof works. So what I'm saying is that when the derivative is defined or something, this is my definition of convex function. Those two you can switch between. I haven't proved it, but I had started with right. So what I'm saying is that if the derivative is defined, then you can convert, you can go between these two definitions. Okay. When your function is super nice, these two definitions are equivalent. Okay? And I only gave a picture, kind of just with this, I just gave you an idea of why this equivalence makes sense.
How is X star local optima?
Oh, I started with a local optima.
You assume that it
It's a local optima, and I have shown that for any y in the domain, it's a local optima. Then for any point y, fy is greater than fx star. That means it's also a global optima. That's what I wanted to show, right? So this implies oh, you are saying that it is coming from the other side. You have to just take care of some direction. Oh, you have to go from y to x star, right? Like you are going in this direction, this convexity, right? So t less than 0, that will not come as a convex part, right? So we don't have to worry about that. So I just have to show it from one direction.
why both direction local optima you already assumed, right? So any direction you go, it should be
Right, but then this should not be y minus x star. This should be x star minus y or something. Because
if you approach X star from any direction, f of X star plus something small should be greater than f of X star.
no, but in this equation, no, limit will evaluate to 0.
Limit will have to derivative, some derivative kind of thing which you wrote there. The limit will.
No, why would limit evaluate to 0? That's not correct.
From the positive side it will be positive, from the negative side.
Oh, right.
Oh, you are saying that this quantity is 0.
At the minimum.
That statement signifies a lot more if you are at local minima, that's fine. So I think the main thing was showing, and that was a bit tautological.
I guess going from here to here. No, but his problem is after assuming this, right? This is 0, you are saying. So, so at least one direction of this should be easy. Okay, so we'll worry about the proof of this later, but you believe that this is true, right? That local optima is global optima, right? So what we now know for convex function, minimization, local optima is global optima, and what else? What about the maximum? This will lie at the boundaries. Right? Because you can't have this kind of a shape. Right? And now if you have a linear function, this will imply that your optimal or sum optimal has to lie at a vertex. Right? Because if you take interior point, you have 2 points here. This point is a convex combination. This x star is a convex combination of x1 and x2. Then at least one of them has the value same as x star. right? So I can keep going outside and my value keeps decreasing or keeps increasing, whatever way I want to do it, right? So this shows that for a linear function, the optimal will lie at a vertex. Sorry? Oh, no, no, no. Now I am thinking of linear function. It is optimizing over a feasible set. Convex set. Okay? So if I am optimizing a linear function over a convex set, then my optimal has to lie at there might be multiple optimals, at least one of the optimal has to lie at the vertex. Sounds good? Okay? And is a global optima, right? Knowing these two, what is a simple dumb algorithm? Right. How to do it is a different question, but what I can do is I can go over all possible vertices, look at all possible values and find the minimum or maximum. But that is obviously, yes, because the number of vertices could be exponential, right? But then we also realize that since local optima is a global optima, that means if I start from any vertex, I always have a direction to move, right? I can always move in a direction where I get to an improvement, right? So then this suggests an algorithm. Move to another vertex. Okay? So this is the idea, and this is called the simplex algorithm. Okay? There are many things which are not defined here. How do I start with a vertex? Right? How do I know that there is a direction of improvement, but why should it be an edge? And which edge should I take? Okay, and the other thing is, why does this have to stop after small number of steps? Okay, what we know is that we still don't have any proof of efficiency of this algorithm. Okay, for whatever natural simplex algorithms people have designed. So again, these three steps can be defined in multiple ways. For all those ways, there are always counterexamples which run in exponential time. But those are kind of boundary cases. For most of the natural cases, simplex algorithm works in polynomial time. So people are pretty happy. Many of the industries still use simplex algorithm to solve any linear program because it works well in practice. Not the dumb one of looking at all the vertices, but this intelligent moving around. So this is from Danzig. I think this is 1948 or something, so it's up 60 years old, 70 years old, but still works well in practice. So now what we want to see is how to implement this thing. Okay? We will see an implementation, but still I can tell you this is not, we don't know whether it is polynomial time. If you show simplex algorithm there is some version of simplex algorithm which is polynomial time, it will be a huge result. This is still open. Okay? But what we want to focus on is one way to implement this. Okay? And that will tell us a lot about the structure of a linear program. Okay? This is the plan for next two classes. Oh, now realize that, so take a minimum, let's say. So in the minimum case, it's a I will consider that my linear function is convex. So if I take 2 points, I can write them as a convex combination of 2 points, then at least at one of the points, the value should be lower. If at this value it is higher, if at this value it is higher, then by convexity property, the value at this will be higher. Like you have to take the correct direction, convex or concave, but now since it's a linear function, it is convex as well as concave. So with this, either x1 will be a direction of improvement or x2 will be a direction of improvement. And I keep doing this, I reach the boundary, I reach the edge, I reach the vertex. Sorry?
It's the same thing we are doing in graph, right? Like in the starting classes, we are finding the point of intersections.
Yeah. But now we have to do it in multiple directions, and we have to realize what does it mean to move in a direction, right? Yes. You mean the graphical approach, we can do it like easily because, yeah, we know where direction to. Okay, thank you.